Drew Stommes. He's a graduate student at the Department of Political Science at Yale University, where he researches the intersection of conflict and elections in South Asia. Drew, please go ahead. The floor is yours.
Great. Can everybody hear me?
Yeah.
Excellent. So thanks for letting me present at this conference. I'm really excited to present some joint work with you today that I've been doing with P.M. Arnaud and Frederic Xavier, where we look at the reliability of published findings using the regression discontinuity design in political science. So just to give you a sense of where I'm going to go with the talk today and some of the key takeaways, the first is that I'm going to show that the existing body of published RD results in political science exhibits characteristics consistent with publication bias. Many studies systematically understated the uncertainty of their treatment effect estimates. Retrospective power analyses suggest that most RD studies in political science were underpowered to detect all but large effect sizes. And as a result, many of the published RD results in political science are spurious. So the RD design has grown immensely in popularity in political science and in the social sciences more broadly, as researchers are attracted to the design's weak identification assumptions, which can be justified through different substantive and institutional knowledge, which supports the core assumptions. Prominent applications of the design in political science include a study of the effect of incumbency on control over the media, and another study that looks at the effect of electing extremist candidates in US congressional primaries on parties' general election performance. So despite the attractive properties of the RD design and the well-justified reasons for using the design in political science, my colleagues and I recognize that there are numerous challenges with actually estimating RD effects that are not necessarily fully acknowledged in the applied literature in political science. So in particular, estimating a treatment effect in an RD setup, which is defined as the difference in expected outcomes at the cut point C, which determines units receipt or eligibility for treatment, is difficult for the following reasons. The first is that there's inherently a bias variance trade-off involved in estimating an RD effect. And the basic intuition behind this is that if researchers are particularly interested in the observations that are close to the cut point, they might be working in a setting where there's negligible, very small, low bias, but because you're using fewer observations, the variance of your estimate is going to increase. And I can illustrate this just with a very brief simulated example. So consider a setting where we have 500 units, and we know that the underlying treatment effect at the cut point is 0.25. So if we estimate the RD effect at the cut point, so 0.5 on this running variable, we can actually have a standard error that's relatively small when we incorporate all of the observations across the support of the running variable. But the challenge with such an estimator is that there's a lot of bias because we are incorporating observations that are quite far away from this cut point. But as we shrink the bandwidth around the cut point, we might be reducing the bias, but as a result, we actually increase the standard error. And so this is a very difficult trade-off to actually navigate in terms of what type of estimator researchers should implement. And so a related challenge with the RD design is that the nominal sample size, so the total number of rows in a data set that a scholar is using, is not necessarily a good indicator of the effective sample size, so the amount of useful information in that data set. And so some implications of these challenges are that the estimation challenge introduces researcher discretion, as there's no intrinsically correct way to estimate RD effects. There are well-motivated ways of estimating RD effects, but it's not like in a randomized control trial where the difference in means is unbiased for the average treatment effect. Additionally, effective sample sizes in RD studies in particular tend to be quite small given the local focus of the estimators. So our contribution in this study is to investigate how these statistical challenges in particular manifest themselves in the body of published RD papers in political science. So I want to raise one caveat before I get into the analysis, and that is we do not evaluate treatment effect identification issues. We focus solely on the estimation challenges associated with the RD design. So if we want to study RD designs in political science, first we need to collect a sample of study that actually uses the design. So we include all applied RD studies published in top political science journals, and specifically, this includes all applied articles that use the design in the American Political Science Review, American Journal of Political Science, and Journal of Politics between 2009 and 2018. We exclude articles that primarily make a methodological contribution to the RD literature because many of these studies used data sets that were previously used in applied studies. And this yields a sample of 45 articles with 10 or more from each of the journals of interest. So next, we needed to collect RD estimates from this sample of articles. And so we have a selection criteria, and that is all results that were referenced in the article's abstract are taken to be the primary results of an article. So basically the results that the researcher wants the audience to pay the most attention to. This yields a sample size of 80 estimates from the 45 articles of interest. We collected a range of study characteristics whenever available. So point estimates, standard errors, p-values, confidence intervals, the bandwidth selection procedure, and the type of RD estimator. So was it a global polynomial, local linear, difference in means, etc. So let's get into what the distribution of original results from these studies actually looks like. So I'm going to show the distribution of t-statistics, so point estimate divided by standard error, among the sample of RD studies. And I'm going to present this distribution in two ways. So the histogram on the left-hand side shows the distribution of t-statistics when we just focus on one estimate per study. The histogram on the right-hand side shows the distribution of t-statistics when we incorporate all of the estimates that were referenced in these articles' abstracts. And ultimately, both histograms tell a very similar story where t-statistics clustered just around and especially to the right of 1.96. This is a distribution of t-statistics that we would not necessarily expect in a healthy body of academic literature. So what might explain this distribution? So there are several possibilities. The first is that there's researcher discretion via bandwidth selection or specification searching, whereby researchers use the estimator that yields a statistically significant result. Or there's publication bias, the file draw problem, where researchers just don't attempt to publish the estimates that are not statistically significant. Or editorial and review processes reject the studies that report null results. Ultimately, all of these possibilities are made worse if scholars are operating in settings which are underpowered and perhaps using inappropriate methods for estimating RD effects. So to evaluate researcher discretion, we're going to focus on researcher discretion via bandwidth selection. So different bandwidth selection procedures offer varying levels of researcher discretion. So we have automated bandwidth selection procedures that select perhaps a mean squared error optimal bandwidth, or arbitrarily selected bandwidths where the researcher has a wide degree of latitude in terms of the bandwidth that's used. And so we're going to compare whether researchers exploit this discretion when implementing arbitrary bandwidths in particular. And so I'm going to show the distribution of t-statistics based on the bandwidth selection procedure. And we would expect that if we would expect that the studies which used an automated approach would exhibit less of a spike around and to the right of 1.96 than the non-automated studies if there were p-hacking via bandwidth selection. And ultimately, what we find is that among the studies that use an automated approach to bandwidth selection, exhibit a drastic spike just to the right of 1.96. And we do see clustering around and to the right of 1.96 for the arbitrarily selected bandwidths, but the pathological feature really comes through when looking just at the studies that used automated bandwidth selection procedures. So to get into the other possibilities regarding what can explain the original distribution of T statistics, we're going to reanalyze the RD studies that are in our sample. And so our approach involves reevaluating all studies that have replication data using a modern approach to RD estimation, so RD robust. And this is going to serve two purposes. The first is that it provides additional insights about researcher discretion by holding the estimator constant across studies. And it's also going to address challenges regarding finite sample estimation in RD settings, because RD robust implements a robust bias correction that accounts for the bias that creeps into RD estimators. So we reanalyzed 36 of the 45 studies in our sample. We were able to, that's the number that we were able, for which we were able to obtain replication data. And we did this by accessing public databases, downloading replication materials from authors' websites, and directly contacting authors when the data were not initially made available online. So our approach to this reanalysis is going to follow recommendations made by Colonico et al. When we reanalyze all these studies. And in particular, this approach selects a mean squared error optimal bandwidth around the cut point. It estimates a linear regression within the bandwidth of the following form, along with applying triangular kernel weights to each of the units. And it incorporates a bias correction for point estimation and accounts for the correction's variability when estimating the standard error. So in practice, this means using the default RD robust settings. So let's get into the results. So I'm going to show the distribution of T statistics for the 25 studies that did not originally use RD robust in the first place. So the distribution for the studies for which we might expect the distribution to shift. So as you can see, the histogram on the left-hand side shows that the T statistics are originally clustered around and to the right of 1.96 for these 25 studies, very similar to the distributions I showed at the beginning of the presentation. And as we incorporate as we re-estimate all of these studies using RD robust, we find that this distribution shifts drastically to the left, and especially to the left of 1.96. So ultimately, what does this reanalysis tell us? What can we take away from it? The first is that, and I didn't show this in the previous slide, is that point estimates don't drastically change when we re-estimate these studies using RD robust, but standard errors systematically increase, especially when incorporating the added imprecision introduced by the bias correction. And so a probable explanation for our original finding that there's this skewed distribution around 1.96 is that there's selection pressure on what type of result gets reported and published. So selection pressure for significant results, however, in a body of poorly powered studies could actually make most of the reported results spurious. So insignificant estimates with non-zero effects could be false negatives, and the proportion of false positives that are published could be disproportionately large. By contrast, if the body of research is well powered, the studies with non-zero effects will be true positives, which diminishes the proportion of published false positives. So we're going to approach this question by conducting retrospective power analyses for all 36 studies that we have for which we have replication data. And this involves 64 point estimates among the total 80 that were in our sample. So we're going to apply the power analysis method implemented in the R package RD Power developed by Cataneo, Tatunik, and Vasquez-Are. And what this is going to do is estimate the power of a two-tailed test at a 5% significance level based on a central limit approximation for the sampling distribution. And so the power analysis presumes that studies will be analyzed using the estimator implemented in RD Robust. So we're going to investigate the power for 4 different effect sizes, 4 different assumed effect sizes ranging from small to large. And we're going to derive these effect sizes by taking the standard deviation of outcomes for control units within the RD Robust bandwidth, and then multiply that standard deviation by 0.1 for the smallest effect, all the way up to 0.8 for large effects. So let's get into the results. So in this table, the column on the left-hand side shows the different effect sizes, and the column on the right-hand side shows, for a given effect size, what is the proportion of studies that achieves 80% power. We find that when we assume the smallest effect size of 0.1, only 13% of the studies achieve 80% power. And with a marginal increase of the effect size, we still remain under 20% of the studies that are that have 80% power. And even when we have moderate to large effect sizes, a substantial proportion of the studies still don't achieve 80% power. So it's only under this largest assumed effect size that we have over 2/3 of the studies being sufficiently powered, but even then, over 30% of the studies are insufficiently powered. So what are some of the main takeaways from this overall exercise and the reanalysis? The first is that the body of published RD research in political science exhibits features consistent with publication bias. The second is that most studies were underpowered to detect all but large effects. And many published RD results in political science that use the design are spurious. We have some forward-looking recommendations, and the first is that while research treatment effect identification is important and an attractive property of the RD design, researchers must be much more cognizant of the estimation and inference challenges in RD settings. And so statistical power is oftentimes going to be a first-order concern with the RD design, and so researchers must ensure that they're working in settings which have sufficiently large sample sizes. And ultimately, investigating statistical power and studying RD effects should involve the use of pre-analysis plans in order for researchers to not feel tempted to select those RD estimates that yield statistically significant results, especially when looking at multiple outcomes. And additionally, journals should take statistical power concerns into account when making publication decisions. So with that, I thank you and welcome your questions and comments.
So there's a lot of action in the chat, so I would invite Abel to select some of your comments and start the conversation.
Sure, this is great. I mean, great paper, and it's amazing you went through the replication packages one by one. Just be careful. I think you're estimating z-stats, not t-stats. So you're gonna have a lot of you're gonna have to de-round those. And I think you don't necessarily have to, because you've been able to actually recompute the true t-stat from the statistical package. So you're not gonna have a lot of measurement there, which is great, because usually you would have a lot when you do this type of analysis. I think, this came up in Joel mentioned the same. I was going to say, if you're using a comment that people back then didn't have access to, it's unclear to me, like I understand why you're doing it, but at the same time, they were not able to do it. So I'm not sure what we're learning here. They're not kind of yakking, they didn't really have access to that. So maybe when you do that exercise, you want to cut the sample. I don't know, but I had a very similar comment to Joel. Anyway, I'll let the floor to other people.
Yeah, so could I briefly respond? Sure. So yeah, one thing that I will say about that is I think the distribution of histograms where we compare studies that used automated versus non-automated approaches to RD estimation sheds light on how even in settings where people were using methods that were relatively modern, so like the researchers that were using the automated approach, we do find that there are these pathological characteristics in the distribution. And even among those researchers that were using the most modern RD methods, we still find that there is insufficient statistical power. And so I think despite the advances in the methodological literature in RD, I don't think applied researchers have quite caught up in terms of acknowledging the extent to which RD designs are data hungry and the extent to which we really need to take statistical power into account, even if we're using the most modern estimators. And
then,
I think
but then you're sorry.
And I think that's what we show through both the power analyses and then in looking at the studies that use automated approaches to begin with.
Okay, but then I think your paper then is not about p-hacking. It's about how much of these were false positives, which is a very different spin. And then looking at distribution of test statistics at the cutoff of 1.86, not that useful. And this is one of the things I wrote in the comment. I think what's interesting is more those that become well-estimated zeros that were actually complete false positive. Whereas if you find that those that are just past the 0.05 threshold and become significant at say the 10%, don't really care about those because they never really have access to that technique, or like they're still significant. So I think it's really more a story of how many of those are really false positive and become well-estimated zero. And you have a bunch, it's quite nice, but I think the spin on the paper then is a bit different.
So one of the things that I'll just very quickly respond is that when we look at the distribution of T statistics and we find that there's this publication bias, ultimately, like we wouldn't be as concerned about the publication bias if those estimates are well powered. And so I don't think we can necessarily have a discussion of statistical power without at least acknowledging that there's this underlying publication bias of some sort. But the point is well taken, definitely.
I think we have time for one more question. Donald Green, yes, go ahead.
Do you have it's a very interesting presentation. Do you have a slide in your deck that just shows a scatter plot of the originally reported estimates and your reanalyzed estimates? Can we just kind of get a sense of how similar they are, or whether they fall along like a 45-degree line, or are they kind of moving all over the place?
Yes, so we have funnel plots, and I can show those. Great, so the left-hand side shows the originally reported estimates, and the plot on the right shows when we use RD robust with the robust bias correction. And ultimately, we find that many of the estimates that were initially just below 1.96 as a result of standard errors being inflated across that 1.96 threshold.
All right, so there's been
just quickly,
yeah.
I think some of those have just kind of exploded. So they're not, it's not really about the 1.96. I would stop like focusing so much on 1.96. I think some of those just like the standard are just exploded here. So these are really false positive. It's not about, oh, now they're significant at only the 10% level. I think it's a much more powerful message. And this graph is great.
Sure, great.
Okay, and there's also some other comments in the chat that we're happy to share with you if you don't have them after the presentation. But thank you very much for the presentation, Drew. Thank you, Max. Thank you, Megan. It has been a very exciting panel. And this basically wraps it up for today.